What came before the Big Bang? What if the Big Bang wasn't the beginning at all? For decades, scientists have described that first blazing moment as the birth of space and time, yet questions linger in the shadows. Was there a universe before ours, hidden in cycles of expansion and collapse? Could black holes hold the seeds of new realities? Or does the very idea of before lose meaning when time itself may have started at the Big Bang? From ancient myths to modern physics, thinkers have wrestled with these mysteries, each theory pulling us deeper into a cosmic riddle. The search for what came before is not just about physics, it's about the limits of human imagination and how far we dare to look into the unknown. Stay with us, and together we'll uncover the most fascinating possibilities of what might have existed before everything began, before time had a name, before the first stars ignited, before galaxies swirled into vast shapes. There was a silence so complete that it defies the imagination. Scientists often say the universe began with the Big Bang, nearly 13.8 billion years ago. But what lingers like a shadow behind that event is the question of what came before it. The difficulty begins with the word before. Time itself is thought to have started with the Big Bang. So to ask what existed earlier forces us into territory where even our language begins to unravel. Yet despite these obstacles, scientists, philosophers, and storytellers have long tried to peer into that hidden realm, searching for clues to a reality that might have preceded everything we know. Albert Einstein's theory of general relativity, published in 1915, gave humanity a tool to describe the structure of space and time as a single fabric. That framework works brilliantly for explaining the movement of planets, the bending of light, and even the growth of black holes, but it fails catastrophically when pushed back to the first instant of the universe. At the singularity, where equations predict infinite density and temperature, the mathematics break apart. Instead of revealing a clear picture, the numbers collapse into nonsense. This failure has led many physicists to wonder if the Big Bang was not a true beginning, but simply a doorway to something older. One proposal comes from quantum mechanics, a branch of physics that took shape in the 1920s with the work of scientists like Niels Bohr and Werner Heisenberg. Quantum theory suggests that at unimaginably small scales, reality is unstable, fluctuating in strange and unpredictable ways. Instead of empty nothingness, there might have been a restless sea of quantum activity. In this view, the Big Bang could have erupted not from a void, but from a quantum landscape that had no clear origin in time. If that is true, the before might not resemble anything like our world, yet it would mean the universe did not appear from nowhere. Other scientists have considered the possibility that time did not simply begin, but has always existed in one form or another. The idea of an eternal universe stretches back centuries, with philosophers like Aristotle arguing that the cosmos had no starting point. In modern physics, versions of this thought survive. The concept of a cyclical universe suggests that what we call the Big Bang could have been one phase in an endless sequence. The universe might expand for billions of years, eventually slow, and then collapse in a big crunch. That collapse, in turn, could ignite another expansion, giving rise to a new cosmos. If this theory holds, then the universe we live in may be only one chapter in an infinite story with no true beginning. Still, the concept of time itself complicates the search. Stephen Hawking, in his 1988 book, A Brief History of Time, argued that asking what came before the Big Bang might be as meaningless as asking what lies north of the North Pole. If time itself was born in that first flash, then before has no definition, because there was no clock to measure anything against. This view can be deeply unsettling, because it challenges the way we understand cause and effect. We are accustomed to believing every event has a trigger, every story has a first page. But the universe may not follow the same rules we expect from daily life. Despite these philosophical challenges, some scientists continue to search for traces that could point backward beyond the Big Bang. In 2010, cosmologist Roger Penrose suggested that patterns in the cosmic microwave background, the faint afterglow of the early universe discovered in 1965 by Arno Penzias and Robert Wilson, might show evidence of a universe that existed before ours. Penrose claimed to see circular imprints that could be scars from black holes in an earlier cosmos. The idea remains controversial, but it shows how even the faintest light left from the early universe can become a map leading into the unknown. The pursuit of what existed before the Big Bang also touches on deeper human instincts. Long before modern science, ancient cultures tried to explain creation by describing what came prior to it. The Babylonians spoke of a primordial sea, while Hindu cosmology described cycles of destruction and rebirth, stretching across vast spans of time called kalpas. These stories may not be scientific, but they echo the same unease felt by today's physicists. The sense that creation must have emerged from something, whether that something was chaos, void, or eternal cycle. The question remains timeless. In the end, when we ask what existed before time had a name, we are really confronting the limits of human understanding. Our tools, equations, telescopes, and even words struggle to grasp a reality where time and space may not have existed at all. The Big Bang gives us a starting point for the story of our universe, but it does not silence the deeper question of origins. Instead, it forces us to consider that there may be mysteries that remain permanently hidden, forever out of reach yet endlessly compelling. What came before may never be answered with certainty, but the search itself reveals something about us, our refusal to accept a boundary without at least trying to see what lies beyond it. Echoes of an earlier universe. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were adjusting a large antenna in New Jersey when they encountered a faint, constant noise they could not explain. What they were actually hearing was the cosmic microwave background, the lingering radiation from the early universe. This discovery earned them the Nobel Prize in 1978, and more importantly, it gave scientists a way to look back in time almost to the moment of the Big Bang itself. Yet within this faint glow, some researchers believe there may be more than just evidence of a beginning. They suggest it could also carry whispers from a universe that came before ours. The cosmic microwave background, often shortened to CMB, is like a fossil of light, stretched and cooled over billions of years. When astronomers map it, they see tiny fluctuations, faint patterns in the temperature and polarization of the radiation. But in 2010, physicist Roger Penrose, alongside Vahe Gurzadian, proposed that some of these patterns might be too regular to have formed in the way scientists usually describe. They suggested that circular imprints in the CMB could be scars left by violent events that happened before our universe began expanding, possibly from collisions of supermassive black holes in a prior cosmos. Penrose's idea was part of a broader theory he called conformal cyclic cosmology. In this view, the universe is not a one-time event that burst into existence, but a repeating sequence of cosmic ages. Each age expands, thins out, and eventually becomes so diffuse that its particles no longer have mass in any meaningful sense. At that stage, time and space lose their ordinary meaning, and a new Big Bang can begin without contradiction. This way, the echoes of what happened in one age could be imprinted faintly onto the next, and we might be living inside a universe that carries the fingerprints of what came before. Not everyone agreed with Penrose. Many scientists pointed out that the circles he identified in the data could simply be statistical noise, coincidences that emerge when analyzing enormous sets of numbers. The Planck satellite, which mapped the CMB in unprecedented detail in 2013, seemed to suggest that the evidence for those circles was not as strong as Penrose hoped. The possibility that our universe could be one in a chain of countless others continues to attract attention, partly because it offers a way to bypass the troubling notion of an absolute beginning. The thought that we might detect signs of an earlier universe is not only a scientific proposal, but also a profoundly unsettling one. If correct, it would mean that events unimaginably far in the past, black holes consuming stars, galaxies colliding, still leave traces in the fabric of our reality today. It would mean that the Big Bang was not a clean break, not the first page of a story, but a continuation of a narrative without end. Hindu cosmology, for instance, describes cycles lasting billions of years, not unlike the scales modern cosmology considers. The difference is that today, instead of poetry and myth, we look for signals in the faint glow of radiation that still surrounds us. Scientists must use careful statistical analysis to decide whether unusual patterns are meaningful or simply the result of chance. In 2020, Penrose reignited debate by linking his theory to the discovery of black hole mergers detected by gravitational wave observatories. He argued that these waves, ripples in space-time itself, might eventually reveal more convincing evidence of echoes from a universe before ours. While his claims remain disputed, the suggestion has kept alive the notion that we are not limited to looking forward into the future of the cosmos but may, with enough precision, glance backward beyond its apparent birth. Even if Penrose's specific predictions prove incorrect, the broader question refuses to fade. Could it be that every Big Bang leaves behind some trace, however faint, that survives into the next universe? Could the patterns in radiation, the faint hum of gravitational waves, or perhaps even the distribution of galaxies, carry subtle hints of events that happened before time as we know it? The more detail scientists uncover in the background light, the more opportunities there are to test whether we are seeing the aftermath of a single beginning or the ghost of something older. What makes this search gripping is not only the scientific stakes, but the human dimension. To consider that our universe might be one of many, that our Big Bang might have followed others stretching back without end, reshapes the way we think about origins. Instead of a singular event, there could be a chain, each universe giving rise to the next, like echoes fading into the distance. Whether those echoes are truly etched into the cosmic microwave background, or whether they remain forever beyond our reach, is still unknown. But the idea itself widens the horizon of imagination. It transforms the Big Bang from the absolute starting point into one note in a much larger symphony, a symphony that may have been playing long before our universe ever appeared. The quantum foam. At the smallest scales of existence, the universe begins to look nothing like the orderly world we see around us. If you take a microscope powerful enough to peer beyond atoms, beyond protons and neutrons, and even deeper into the fabric of reality itself, the picture dissolves into chaos. In the early 20th century, scientists such as Max Planck and Werner Heisenberg discovered that the laws of physics behave strangely when you reach these extreme scales. Energy and matter no longer sit still. Instead, they flicker, vanish, and reappear, as though reality itself is restless. This unpredictable sea has come to be called quantum foam, a term introduced by physicist John Wheeler in 1955. Wheeler described it as the jittery, frothing state of space-time when examined at the Planck scale, an unimaginably tiny size of about 10 to 35 meters. At this level, time and space cannot be treated as smooth and continuous. Instead, they bubble and churn like boiling water. Particles may pop in and out of existence, while space-time itself twists and warps in sudden fluctuations. This chaotic foundation has led some to wonder if the Big Bang itself might have been born out of such a quantum storm, the eruption of order from a sea of restless uncertainty. The idea of a universe springing out of quantum foam is not as wild as it may sound. In the 1970s, physicists began exploring models where quantum mechanics and gravity interact. One suggestion is that virtual particles, which constantly appear and vanish in space, could sometimes become real under extreme conditions. If this process happened at the beginning of time, the entire universe might have been the result of one such fluctuation, expanding rapidly into the cosmos we now inhabit. This theory challenges our understanding of what nothing means, but in quantum physics, even a vacuum is not truly empty. It seethes with energy, with particles briefly existing before vanishing again. In 1948, Dutch physicist Hendrik Casimir demonstrated this reality in a striking experiment. He showed that two metal plates, placed very close together in a vacuum, would experience a measurable force, caused not by anything visible, but by the energy of the vacuum itself. What Casimir revealed is that empty space is alive with activity, and this discovery still shapes how scientists think about the origins of the universe. The notion that our cosmos began from quantum foam raises unsettling questions. If the foam exists eternally, then perhaps universes are constantly being born from it, expanding and evolving, while others collapse and vanish. Some scientists have suggested this could mean there are countless universes beyond our own, each one a ripple formed from the same chaotic sea. Though compelling, this vision rests on uncertain speculation. The Planck scale is so tiny that no current experiment can directly observe it. The physics of quantum foam requires a theory that unites quantum mechanics with general relativity, something researchers have been seeking for decades. Attempts such as string theory and loop quantum gravity try to provide answers, but so far, none have been confirmed by evidence. Still, the concept of quantum foam continues to inspire scientists because it points to a reality where the very building blocks of space and time are not fixed but fluid. For ordinary people, the idea of a universe born from quantum foam can be both awe-inspiring and unsettling. It suggests that the stable world we know rests on a foundation of uncertainty. The same restless energy might once have created everything we see, from the faint glow of distant galaxies to the earth beneath our feet. In that sense, the story of quantum foam is not only about the earliest moments of creation, but also about the hidden movements of the present, the ceaseless activity that never truly stops. The Big Bang, when seen through this lens, is no longer an absolute beginning. Instead, it becomes a sudden emergence from a deeper, chaotic reality. We may never know for certain if this is how the cosmos began, but the thought that an ocean of uncertainty might lie beneath everything we experience changes the way we see the universe. What seems solid may rest on a foundation that is endlessly shifting, a quantum foam that existed before time itself had meaning, and perhaps still ripples beneath every moment we live through. Eternal inflation. At the heart of eternal inflation lies a puzzle waiting to be solved. In the early 1980s, physicist Alan Guth was working on problems related to the very first fraction of a second after the Big Bang. He noticed that certain conditions could cause space to expand at an unbelievably fast rate, faster than anything we normally imagine. This concept, which he published in 1981, became known as cosmic inflation. According to his calculations, this rapid expansion would have smoothed out the young universe, explaining why the cosmic microwave background appears so uniform no matter where we look. It solved some long-standing mysteries in cosmology, but it also opened a door to a far stranger possibility. Inflation, as Guth described it, was not necessarily a one-time event. In the years that followed, other scientists, including André Linde, developed the idea further. They found that while inflation might have ended in our observable universe, it could still continue in other regions. Space, instead of inflating everywhere at once, might have patches where the process never stopped. If this is true, then our universe is only one bubble in a much larger cosmic sea. Beyond what we can see, new bubbles would constantly be forming, each with its own laws of physics, each expanding into its own vast cosmos. This never-ending process is what scientists now call eternal inflation. The image of a universe made up of countless bubbles is both beautiful and unsettling. In our bubble, stars form, galaxies spin, and life emerges on small planets. But just beyond the horizon of what our telescopes can detect, there could be other bubbles, unreachable and forever separate from us. Some of these universes might resemble our own, while others could be so different that the very building blocks of matter take unfamiliar forms. The thought that our universe is only one of many changes the way we see ourselves, reducing the sense that we occupy a unique place in the grand story of existence. One of the strange features of eternal inflation is that it leaves almost no room for a true beginning. If inflation continues endlessly, then there may have been universes before ours, and there will certainly be others after. The Big Bang we experience might be only a local event, one moment in a process without end. Some scientists argue that this view removes the need for a singular origin, replacing it with a landscape of universes constantly being born. It shifts the question of what came before into something more complicated, not a single answer, but an endless chain of cosmic creations. Evidence for eternal inflation is difficult to pin down, since by definition, other universes lie beyond our reach. Yet scientists search for clues in the cosmic microwave background and in the distribution of galaxies. Some have even suggested that collisions between our bubble and another could leave subtle marks in the sky, patterns in radiation that betray a cosmic encounter billions of years ago. While no such evidence has been confirmed, the mere possibility fuels research, since it would mean that our universe once brushed against another, leaving a faint scar in the heavens. From a philosophical perspective, eternal inflation holds consequences that are difficult to ignore. If countless universes exist, each with its own conditions, then the fact that we live in one suited for life might not be a miracle, but a necessity. In such a multiverse, all possibilities could be realized somewhere, and we simply find ourselves in the universe where beings like us can exist. This reasoning, sometimes called the anthropic principle, has been both embraced and criticized. Some scientists see it as a practical way to understand why our universe is the way it is, while others argue that it drifts too far from testable science. Although debates persist, the idea of eternal inflation stands out as a striking explanation for what preceded the Big Bang. Instead of imagining a single moment of creation, it presents a picture of a reality that is always creating, always expanding, always bubbling with new worlds. Our universe, with all its history and beauty, becomes one among countless others, a fleeting event in an infinite cosmic landscape. Whether or not evidence will ever prove this theory, the vision it offers is extraordinary. A universe without borders, without a true beginning, and perhaps without an end. The cyclical universe. Long before modern telescopes and satellites, people tried to imagine what the universe might be and how it began. In ancient India, Hindu thinkers described cycles of creation and destruction lasting billions of years, a rhythm of endless renewal. The Stoics in Greece also believed the cosmos burned itself out in fire and was reborn again, repeating this cycle without end. These stories were not based on scientific measurements, yet they reflected an intuition that creation might not be a single event, but part of a repeating pattern. Modern physics, surprisingly, has returned to a similar possibility, suggesting that the Big Bang may not have been the first time a universe came into being. It was in the 20th century that the idea of a cyclical cosmos became scientifically serious, as physicists considered a future slowing of expansion. In 1929, Edwin Hubble showed that distant galaxies are moving away from us, evidence that the universe is expanding. If gravity were strong enough, scientists reasoned, this expansion could one day stop and reverse. The result would be a big crunch, where everything collapses back into a dense state, not unlike the conditions thought to exist at the Big Bang. From that collapse, a new expansion could ignite, creating another universe. In this view, our cosmos might be only the latest in an infinite series of births and deaths. Later discoveries complicated the picture. In the late 1990s, astronomers studying distant supernovae found that the expansion of the universe is actually accelerating, driven by what we now call dark energy. This made the idea of a future collapse less certain. If expansion continues to speed up, then a big crunch seems unlikely. Still, physicists did not abandon the cyclical concept. Instead, they began to imagine other ways the universe could renew itself. Some suggested that the acceleration we see today could eventually slow and reverse if the nature of dark energy changes over time. Others proposed that even without collapse, there could be mechanisms allowing the universe to contract and rebound, a bounce that repeats forever. One of the most ambitious versions of this theory is the ekpyrotic model, introduced in the early 2000s by Paul Steinhardt and Neil Turok. They suggested that our universe might be part of a larger, higher-dimensional reality. In this scenario, what we see as a Big Bang could actually be the result of two vast brains colliding in higher-dimensional space. Each collision triggers a new cycle of expansion and evolution, repeating endlessly. While this idea is speculative, it shows how modern physics continues to search for ways to describe the universe as part of a grand repeating cycle rather than a single event. The strength of the cyclical model is that it engages directly with the profound question of why the universe is so precisely arranged for structure and life. If there have been countless cycles, then the conditions we see today may not be a one-time coincidence, but the result of repeated resets. Each cycle would erase much of the previous history, but traces could linger, faint imprints that might one day be detected. Some scientists have even looked for such signs in the cosmic microwave background, hoping to find patterns that hint at a universe older than our own. Of course, there are challenges. The second law of thermodynamics tells us that entropy, or disorder, tends to increase over time. If the universe were truly cyclical, with an endless sequence of expansions and contractions, then entropy should build up across cycles, making each one less ordered than the last. Some versions of the theory attempt to solve this problem by suggesting that entropy is reset during each collapse or bounce, wiping the slate clean. Whether this mechanism could really work remains one of the open questions in cosmology. Even with these uncertainties, the cyclical universe remains one of the most haunting answers to the question of what came before the Big Bang. It allows us to imagine a reality with no true beginning and no end, a cosmic heartbeat pulsing across eternity. Our own lives, short as they are, would unfold in only one cycle among countless others. The galaxies above us, the Earth beneath our feet, even time itself might be temporary arrangements in an ongoing rhythm that stretches beyond memory or imagination. Whether science one day proves or disproves this vision, the thought itself carries a quiet power, reminding us that the universe may be less like a straight line and more like a circle, endlessly turning through ages without number. The cosmic bounce. Imagine the universe not as a story with a single opening line, but as a tale that pauses, folds back on itself, and then begins again in a new form. This is the essence of the cosmic bounce, a theory that suggests our universe may not have started from nothing at all, but instead emerged from the collapse of a prior cosmos. Rather than a singular beginning, reality may be engaged in a cycle of contraction and rebirth, where each Big Bang is also the aftermath of a previous universe coming to an end. At its foundation is the fact that Einstein's equations accommodate both cosmic expansion and collapse. While Edwin Hubble's 1929 discovery showed that galaxies are racing away from one another, the mathematics of general relativity never ruled out the opposite motion. If gravity became dominant enough, the expansion could reverse, drawing everything together into what scientists once called the Big Crunch. For much of the 20th century, cosmologists debated whether the universe would expand forever, balance on the edge, or collapse back into a fiery end. Out of this debate came the seed of a new possibility. What if the collapse was not the final chapter, but the trigger for something new? In a bounce scenario, the unimaginable density of a collapsing universe does not remain trapped in a singularity, where equations break down and no further description is possible. Instead, the collapse creates conditions that force a rebound, releasing energy in a sudden expansion we now recognize as a Big Bang. Our universe, then, would not be the first, but part of an endless sequence of universes born from the collapse of their predecessors. This view changes the question from what happened before the Big Bang to how many bounces have there been, and what traces did they leave behind. One of the difficulties with the bounce concept has always been entropy. The second law of thermodynamics insists that disorder increases with time. If universes collapse and bounce repeatedly, then entropy should accumulate from one cycle to the next, leading to a cosmos too chaotic to reset. To address this, some theorists proposed that the bounce is not a simple rebound, but involves mechanisms that dilute or reset entropy. In the early 2000s, researchers Paul Steinhardt and Neil Turok developed a version where each bounce is tied to collisions in higher dimensional space, preventing entropy from building endlessly. Their work, while speculative, gave new life to the idea that the universe could have experienced countless cycles without collapsing into disorder. There are also models grounded in quantum physics that support the bounce idea. Quantum mechanics, with its restless fluctuations, suggests that space and time may resist true singularities. Instead of a point of infinite density, the end of a collapsing universe could transform into a phase of rapid expansion. Loop quantum cosmology, developed by researchers such as Martin Bojawald, explores this possibility by applying principles of loop quantum gravity. In this framework, the Big Bang is not a beginning, but a bounce, a transition where gravity turns repulsive at extreme densities and prevents collapse from reaching a singular point. If the cosmic bounce is correct, then our universe may carry hidden scars of what came before. Some cosmologists search the cosmic microwave background for unusual patterns, faint signals that could reveal traces of a previous contraction. While no definitive evidence has been found, the search continues, as even the smallest irregularities might provide clues about a universe that existed before ours. The possibility that we live in the aftermath of a cosmic rebound is difficult to prove, but it remains one of the more compelling alternatives to the idea of a singular beginning. For those who contemplate it, the cosmic bounce reshapes the way we see time. Instead of a straight line stretching back to an origin, time could be cyclical, with each universe inheriting the ashes of the one before. It offers a vision of reality that is not fragile, not perched on a single improbable beginning, but resilient, capable of renewing itself again and again. Whether through the mathematics of relativity, the speculations of higher dimensions, or the quantum laws that prevent true collapse, the bounce suggests a universe with a deeper story, one that stretches far beyond the moment we call the Big Bang. The role of black holes. When scientists first began to take black holes seriously in the mid-20th century, they were seen only as dead ends, places where matter and light were trapped forever, with no chance of return. Albert Einstein's equations of general relativity had hinted at their existence as early as 1916, and by the 1960s, astronomers like John Wheeler popularized the term black hole. Yet even as their presence in the cosmos became more accepted, the question of what actually happens inside remained unanswered. To many, black holes were tombs of stars, the final resting places of collapsed giants. But others began to wonder if these mysterious objects might hold something far stranger, perhaps even a clue to what existed before our universe began. The defining feature of a black hole is its event horizon, the invisible boundary beyond which nothing can return. Inside, the pull of gravity becomes irresistible, and according to classical theory, matter falls inward until it is crushed into a singularity, a point of infinite density where time and space cease to behave in any meaningful way. This is where the physics we know collapses, and it is here that speculation about new beginnings often takes root. If the singularity is not the end of the story, then it might act as a gateway to something else. Some researchers have suggested that what falls into a black hole could reappear as the birth of a new universe, hidden away from ours, and carrying its own laws of physics. In the 1980 and 1990, thinkers like Lee Smolin advanced the idea that black holes could be seeds of creation. He proposed a concept sometimes called cosmological natural selection, where every black hole might give rise to a new universe on the other side of its singularity. Each of these baby universes could have slightly different physical constants, and the ones that produce many black holes would, over time, become more common. In this view, our universe exists not by chance, but because it is particularly good at producing black holes, and therefore descendants. It is a daring way to think about origins, one that replaces the singular Big Bang with a branching tree of universes. Other models take a more mathematical approach. In some interpretations of relativity, the interior of a black hole is not a one-way collapse but a kind of passage, a wormhole leading elsewhere. If such a connection could exist, then the collapse of matter in one universe could create a burst of expansion in another, resembling a Big Bang. While wormholes are still theoretical and unproven, the possibility keeps resurfacing because it offers a way to bridge the gap between an ending and a beginning. Even though most physicists remain cautious, the attraction of the idea is hard to ignore. Black holes, the most destructive objects we know, could also be the cradles of new creation. So far, no clear evidence has been found. The information paradox, famously raised by Stephen Hawking in the 1970s, highlights how black holes do not fit neatly into our understanding of physics. According to quantum theory, information about matter should never be lost, yet black holes seem to erase it completely. This puzzle has pushed researchers to reconsider what really lies inside. If information is somehow preserved, then it could be carried through to whatever lies beyond a singularity. In that sense, black holes would not only destroy but also transmit, passing fragments of one universe into the seed of another. The thought that our own Big Bang might have been born inside the heart of a black hole from another cosmos adds a layer of wonder to what we see in the night sky. Every black hole scattered through the Milky Way, from the supermassive one at the center named Sagittarius A, times to the smaller stellar remnants catalogued in the 2010, could be more than just celestial graves. They might be silent engines of creation, building new realities beyond our reach. For now, No telescope can peer beyond an event horizon to confirm these ideas, but the mystery continues to draw attention. The first image of a black hole, captured in 2019 by the Event Horizon Telescope, gave humanity a glimpse of the shadow where light itself vanishes. Yet behind that shadow may lie something far richer than eternal darkness. It may conceal the possibility that the end of one story becomes the prologue to another, where every collapse carries the promise of a new beginning. The nothingness question. When people try to picture what came before the Big Bang, one of the most common images that comes to mind is absolute emptiness. A state of nothing at all, without space, without time, without matter or energy. Yet the more scientists and philosophers have tried to grasp this idea, the more slippery it becomes. The human mind is trained to think in terms of things, shapes, sounds, moments, so when we are asked to imagine nothingness, it quickly turns into something after all, like a blank black canvas or a quiet room. True nothingness, the complete absence of everything, resists being pictured, and this difficulty has haunted cosmology for centuries. The ancient Greek philosophers were already struggling with the concept. Parmenides, around the 5th century BCE, argued that nothing could not exist, because even to speak of it gave it a kind of presence. Aristotle later echoed this idea, claiming that nature abhors a vacuum. Fast forward to the 17th century, and the invention of air pumps and experiments with vacuums seemed to suggest that space could be created. But even then, the emptiness was filled with pressure, forces, and the potential for matter. The question remained unresolved. If our universe came from nothing, what exactly was that nothing? Modern physics complicated the matter even further. In the 20th century, when quantum mechanics began to take shape, scientists like Werner Heisenberg and Paul Dirac showed that what we call space is far from empty. Even a vacuum contains fleeting particles that flicker in and out of existence, a restless background energy sometimes called quantum fluctuations. This suggests that if the universe did come from nothing, the nothing must be more active than we usually imagine. The problem lies in language as much as in science. In physics, when researchers like Lawrence Krauss or Stephen Hawking have spoken about the universe arising from nothing, what they often mean is a vacuum state governed by quantum rules, which still has structure and laws. Critics have pointed out that this is not truly nothing at all, but rather a kind of something stripped to its minimum form. The question then becomes whether absolute nothingness can exist in any meaningful sense, or whether it is always replaced by some background framework. Some thinkers have even suggested that the very idea of nothing is an illusion. In 1922, the philosopher Martin Heidegger asked, "Why is there something rather than nothing?" It became one of the central questions of metaphysics, driving debates about whether existence itself requires an explanation. For cosmologists, this line of thought translates into another puzzle. If nothing is impossible, then perhaps the universe could never have failed to exist in some form. Physics tries to build models that can be tested, often through mathematics and observations, like the patterns of cosmic microwave background radiation first detected in 1965. Philosophy, on the other hand, deals with the meaning of concepts like nothing and being, which cannot be captured by instruments or equations. Yet the two fields meet at this frontier, where the birth of the universe forces us to consider what we mean by absence in the first place. Some scientists lean on the idea of symmetry breaking, where even if the universe began in a perfectly balanced state, tiny instabilities caused it to expand into the cosmos we see today. In this sense, the universe may not have emerged from nothing, but from a fragile balance that tipped into motion. Others point to the laws of physics themselves, wondering whether these laws existed before the universe, or if they too were created in the act of expansion. If the laws predate the universe, then the nothingness question shifts again. Perhaps nothingness is not possible because the laws of nature are eternal. The most unsettling part of the discussion is that it may be unanswerable. Our minds evolved to think within space and time, to measure distance, weight, and change. Asking us to conceive of a state before space and time, where none of these measures apply, may be like asking a fish to imagine dry land without ever leaving the sea. The thought that there might have been a true nothing before the first burst of creation forces us to face the limits of knowledge, and at the same time, the mystery of existence itself. Whether the answer lies in physics, in philosophy, or beyond both, The question of nothingness remains one of the most haunting puzzles connected to the Big Bang. Even if we never resolve it, the act of asking reminds us that the universe is not only a place of stars and galaxies, but also of mysteries that defy even the boldest imaginations. Ancient myths and early visions, centuries before telescopes scanned the heavens or equations filled chalkboards, people sought to unravel the mystery of the world's origins. Every culture carried its own story, passed from one voice to another, often told around firelight or in sacred spaces. These stories were not written to be tested or measured, but they carried meaning, giving structure to the unknown and helping communities explain their place in a vast, often frightening universe. The stars, the sea, and the mountains became symbols, and in them, people found clues to the beginning of all things. One of the oldest surviving tales comes from Mesopotamia, written down on clay tablets around 1100 BCE. In the Babylonian story called the Enuma Elish, creation began not with light or form, but with the mingling of two primeval waters, Apsu and Tiamat. From their union came the first gods, and from conflict among these gods the world was shaped. Marduk, a storm deity, defeated Tiamat and split her body in two, making the heavens and the earth. For the Babylonians, the birth of the universe was inseparable from the struggle of order against chaos, and the cosmos itself was seen as a victory over destruction. Across the Mediterranean, the Greeks told stories that echoed similar themes but with their own imagery. Hesiod, writing in the 8th century BCE, described how everything began with chaos, not as a storm but as a formless gap, an emptiness. From chaos emerged Gaia, the earth, and then Eros, the force of attraction that bound beings together. Soon came the sky, the mountains, and the seas, each taking shape as living presences. For the Greeks, the cosmos was not created from nothing, but grew from an eternal void into a living family of powers, each with its own will and character. In India, verses of the Rig Veda, written around 1500 BCE, contained hymns that speculated about the origins of existence. One hymn asked whether even the gods knew how creation began, since they came after it. Another suggested that in the beginning there was only darkness wrapped in darkness, until heat and desire stirred and gave rise to life. Unlike other traditions that offered firm answers, these verses left the question open, embracing uncertainty as part of the mystery itself. The idea that the beginning could be unknowable still resonates today, echoing in the way modern science grapples with questions of what came before the Big Bang. The myths of Egypt told of a different kind of birth, one rising out of water and light. Around 2400 BCE, priests in Heliopolis taught that the sun god Ra emerged from the primeval waters of Nun and brought order by speaking the world into being. In another version, the god Atum rose from a mound of earth and created other gods through his breath and actions. The Nile's yearly flood made water a natural symbol for the unknown beginning, since it both threatened destruction and guaranteed fertility. The cycle of life, death, and renewal was woven into the Egyptians' vision of the cosmos. Far across the ocean, in the Americas, creation stories also took root. The Maya of Central America, recording their myths in the Popol Vuh during the 16th century, described how the gods attempted several creations before succeeding. The first beings of mud crumbled away, the second of wood lacked spirit and respect, but the final attempt, using corn, gave rise to true humans. In these stories, creation was not a single moment, but a process of trial, error, and persistence, a reflection of the deep importance of maize in sustaining their daily lives. Among the Norse, tales recorded in the Poetic Edda around the 13th century spoke of a yawning void called Ginnungagap, flanked by realms of fire and ice. When the two met, the giant Ymir was formed, and from his body the world was shaped. His flesh became the earth, his blood the seas, his skull the sky. The myth revealed a vision of the universe as both violent and fertile, born from extremes and balanced through transformation. Each of these ancient visions carried its own landscape, gods, and symbols, yet they all spoke to the same human desire to find meaning in the unknown. Whether it was water, chaos, darkness, or void, the starting point was never truly nothing. It was always something vast, shapeless, and powerful, waiting to be stirred into life. What these stories share with modern attempts at cosmology is the recognition that the question of beginnings is not only about facts, but about wonder. The myths may not offer scientific explanations, but they remind us that humanity has always reached for the mystery at the edge of knowledge, trying to weave it into a story that could be told, remembered, and passed on. The limits of physics. There are moments in the history of science when progress seems unstoppable, when new discoveries follow each other so quickly that the boundaries of knowledge appear to expand without end. At the start of the 20th century, the breakthroughs of Albert Einstein, Max Planck, and Niels Bohr transformed physics into a discipline that felt almost limitless. The theory of relativity reshaped space and time, while quantum mechanics revealed a strange and hidden world at the smallest scales. Together, these frameworks gave humanity the ability to describe stars, atoms, and much in between. Yet even as the triumphs accumulated, cracks began to show. The universe was larger and stranger than anyone had guessed, and the tools that had seemed so powerful began to falter at the edges of understanding. Bringing together Einstein's 1915 theory of general relativity and the later framework of quantum mechanics remains one of science's greatest difficulties. Relativity works beautifully for describing planets, black holes, and the expansion of the cosmos, but it does not fit easily with the probabilistic, uncertain world of particles. When scientists attempt to apply both at once, as in the center of a black hole, or the first moments after the Big Bang, the mathematics breaks down into infinities and contradictions. For more than a century, brilliant minds have sought a unifying theory, but no single approach has yet passed the tests of observation and experiment. Another boundary arises not from theory but from the limits of what can be measured. In 2012, the Large Hadron Collider near Geneva confirmed the existence of the Higgs boson, a particle predicted nearly 50 years earlier. It was hailed as a triumph, but also a reminder of how hard it is to probe deeper. Building machines powerful enough to test new ideas requires extraordinary resources, and even then, there are scales so small and energies so high that no conceivable experiment could ever reach them. The Planck length, roughly 10^35 to 10 circumflex, -35 or 10^35 meters, is often cited as a barrier below which space and time lose their familiar meaning. At that scale, the notion of measuring anything at all becomes uncertain. Cosmology, too, faces its horizons. Telescopes can peer billions of light years away, offering glimpses into the early universe, yet there are parts of the cosmos forever hidden from view. The cosmic microwave background, discovered in 1965 by Arno Penzias and Robert Wilson, serves as a wall of fog beyond which we cannot see with light. What lies before it, or outside the observable universe, remains out of reach. No matter how sophisticated our instruments become, some regions will always be inaccessible, cut off not by technology, but by the nature of space itself. Even within the observable world, mysteries remain. Dark matter, first hinted at by the observations of Fritz Zwicky in the 1930s, outweighs visible matter by a factor of 5, yet has never been directly detected. Dark energy, proposed in the late 1990s to explain the accelerating expansion of the universe, makes up even more. Together they account for nearly 95% of the cosmos, leaving the familiar atoms that compose stars, planets, and people as only a small fraction. Physics has given names to these unknowns, but not yet their true nature. Time itself poses another frontier. Relativity shows that time is not absolute but can stretch or compress depending on motion and gravity. Yet why time seems to flow in one direction, from past to future, remains unresolved. The arrow of time is tied to entropy, the gradual increase of disorder described in the laws of thermodynamics. But the deep reason for this imbalance continues to puzzle scientists. If the laws of physics are mostly reversible, why does reality unfold in a single direction? This question touches not only cosmology but the heart of human experience. For some, these boundaries are seen as obstacles that will one day be crossed. Just as earlier generations once thought it impossible to know the composition of stars, until spectroscopy revealed it in the 19th century. For others, the limits may be fundamental, woven into the very structure of reality. There may be truths that no theory or measurement can uncover, not because of failure, but because the universe is shaped that way. In facing these limits, physics does not diminish but gains a kind of humility. It acknowledges that while human reason has carried us far, from the first myths of creation to the equations that guide spacecraft across the solar system, there may always be mysteries that remain beyond reach. What lies ahead is uncertain. Perhaps new tools will pierce the barriers, or perhaps the edges will shift, but never fully vanish. Either way, the pursuit continues, driven by the same curiosity that has guided humanity since the beginning, a recognition that the horizon may move, but never disappear. Clues hidden in light. The earliest view of the heavens was one of simple beauty stars, as pinpoints of light, remote and unwavering. Yet hidden in that light were stories waiting to be uncovered. In the 19th century, when Joseph von Fraunhofer carefully examined sunlight through a prism, he noticed dark lines cutting across the rainbow of colors. These lines, later known as absorption lines, revealed that the sun was not a featureless ball of fire but a complex mixture of elements. Each atom left its own fingerprint in the light, and with this realization, the stars ceased to be unknowable lanterns in the sky. They became objects that could be read, almost like books written in an unfamiliar but decipherable language. As technology improved, spectroscopes allowed astronomers to break down light from distant stars and galaxies into fine detail. By the early 20th century, Cecilia Payne, working at Harvard, made the bold claim that stars were made mostly of hydrogen and helium. Her insight overturned long-held assumptions and reshaped astronomy. Light, something so ordinary in daily life, carried across space the secrets of nuclear furnaces burning millions of kilometers away. From then on, every telescope became not only an instrument for seeing, but for listening to the voices carried in starlight. The importance of light grew even greater in the middle of the 20th century, when Arno Penzias and Robert Wilson stumbled upon an odd hiss in 1965 while testing a radio antenna in New Jersey. At first, they thought it might be caused by pigeons nesting inside the equipment, but after cleaning it thoroughly, the noise remained. It turned out they had detected the cosmic microwave background, the faint afterglow of the Big Bang itself. This light, stretched into microwave wavelengths by billions of years of expansion, filled every corner of the universe. It was like a fossilized memory, a relic of a time when the cosmos was young and dense and hot. Suddenly, cosmology had direct evidence that the universe had once been very different, a discovery that earned them the Nobel Prize and permanently changed our understanding of beginnings. Astronomers also began noticing that light could be shifted, a phenomenon known as redshift. In the 1920s, Edwin Hubble, working with the 100-inch telescope at Mount Wilson, found that galaxies were not static, but moving away. Their light stretched to longer wavelengths as space itself expanded. This discovery provided the first strong evidence that the universe was not eternal and unchanging, but dynamic, growing, and evolving. Redshift became a tool to measure distance and speed, turning faint smudges of light into markers of cosmic history. The story of light does not end with what we see directly. Neutrinos, almost weightless particles born in nuclear reactions, travel through stars and space largely unnoticed, and gravitational waves ripple invisibly across the universe, bending space-time itself. Yet photons, the particles of light, remain our most constant messengers. They are sensitive to the tiniest interactions, and when collected through sensitive instruments, they reveal not only what objects are made of, but also how they move, how hot they are, and sometimes even what their past looked like. In recent decades, space telescopes such as Hubble, launched in 1990, and James Webb, launched in 2021, have extended the reach of human eyes far beyond the atmosphere. Webb in particular has begun to show the earliest galaxies forming just a few 100 million years after the Big Bang. In those faint, stretched-out signals, astronomers are learning how the first stars ignited and how cosmic structures emerged from the smooth glow of the microwave background. Light, delayed by billions of years, arrives as a messenger from times long before Earth itself existed. Even the search for planets around other stars, once thought impossible, depends on light. When a planet passes in front of its star, a fraction of starlight is dimmed, and by analyzing how the spectrum changes, scientists can detect the presence of atmospheres, sometimes even hinting at molecules like water vapor or carbon dioxide. The same method that revealed helium in the sun in the 19th century is now being used to explore the chemistry of worlds that may lie hundreds of light years away. What is striking is how fragile these signals are. A photon can travel across the cosmos for billions of years, only to strike a mirror in a telescope and end its journey by carrying its message to a detector. Each one is a survivor of unimaginable distances, and when gathered together, they give shape to a story much larger than ourselves. Without them, the universe would be silent, its history locked away. With them, even the void between galaxies is filled with information, waiting for patient observers to decode it. Light continues to remind us that the universe does not hide its past entirely, but leaves trails that attentive eyes can follow. The flicker of a star, the faint glow of ancient radiation, the red shift of a galaxy drifting away, all are clues etched across space. They are not easy to read, and they often come faint and scattered, but for those willing to look, they remain the most faithful record of where everything came from and where it is still going. The philosophical abyss. Philosophy has always lingered at the edge of science, where questions grow too heavy for numbers alone. When thinkers in ancient Greece argued about the nature of existence, they were already staring into what might be called an abyss, a place where certainty fades and only speculation remains. Parmenides declared that nothing could come from nothing, while his rival Heraclitus suggested that change itself was the foundation of all things. Neither could prove their vision, yet their arguments shaped how later generations approached the deepest mysteries. The same tension continues today, when physicists and philosophers wrestle with ideas about time, causality, and what it even means for the universe to exist. By the Middle Ages, Christian theologians were struggling with similar puzzles, but placed them in the language of creation. Thomas Aquinas, writing in the 13th century, argued that even if the world had no beginning in time, it still depended on God for its existence. Centuries later, Baruch Spinoza imagined that the universe itself was divine, a single substance with infinite attributes. The abyss remained, only reframed, as people asked whether reality required an external cause or if it was simply all that there is. These reflections may sound distant from modern physics, yet they share the same root: the human need to answer what lies behind everything visible. In the Enlightenment, when reason became the guiding principle, David Hume raised doubts that would echo into modern thought. He questioned whether causation itself was real, or merely a habit of the mind, formed from repeated experience. If cause and effect were illusions, then the chain of reasoning that tried to reach a first cause might collapse altogether. Immanuel Kant followed with his own claim that time and space might not be external features of reality, but frameworks imposed by the human mind. Once again, the ground shifted, and the abyss widened, because the very categories by which we think about beginnings and existence were placed into question. Rather than closing, the abyss grew wider amid the rapid developments of 20th century physics. Albert Einstein's theories of relativity showed that time and space were intertwined, not separate, and that they could stretch, bend, or even end. The Big Bang model introduced a starting point for the universe, yet it raised more questions than it solved. If time itself began there, what does it mean to ask what happened before? Some philosophers argued that the question is meaningless, while others insisted that there must still be an explanation beyond the reach of equations. The strange behavior of quantum mechanics only made the picture more unsettling. In Copenhagen in the 1920s, Niels Bohr argued that reality does not take on definite form until it is measured, while Albert Einstein objected, famously insisting that God does not play dice. The debate revealed how fragile our grasp of reality might be when stripped of everyday assumptions. If existence depends on observation, or if multiple possible outcomes unfold at once, then the abyss yawns wider, forcing us to reconsider whether the universe has a stable foundation at all. Later in the century, philosophers like Martin Heidegger and Jean-Paul Sartre took the problem in another direction. Heidegger asked why there is something rather than nothing, calling this the most fundamental question of metaphysics. Sartre, in 1943, described nothingness as an active presence, not just an absence, shaping human freedom and anxiety. Their ideas were not equations or models, Yet they captured the same unease that physicists feel when contemplating singularities or the quantum vacuum. It is the same abyss, seen from different angles, and no less unsettling for being clothed in a different language. Even today, as telescopes reveal galaxies at the edge of visibility and particle colliders probe the smallest fragments of matter, the abyss persists. The laws we know work with astonishing precision, yet they break down at the boundaries. Inside black holes, at the first moments after the Big Bang, or when quantum mechanics is forced to meet relativity. Philosophers remind us that laws themselves are not explanations but descriptions, and that asking why such laws exist at all may lead beyond science. For some, this abyss is terrifying, a reminder of human limits. For others, it is inspiring, a space where imagination and wonder thrive. Every generation seems to circle back to the same haunting question: is the universe self-sufficient, or does it point to something beyond itself? No telescope can answer this fully, no experiment can close the gap, and yet the pursuit continues. Perhaps the abyss is not meant to be crossed but lived with, a reminder that mystery is woven into the very fabric of existence.